Okay, let's jump right into this explainer. Today, we're unpacking a concept that catches so many people off guard, and that is the limits of accuracy. We're going to uncover why the numbers you see in the real world, and definitely the ones in your math textbooks, are rarely as exact as they actually seem. It sounds simple on the surface, but there are some hidden traps here that can completely derail your calculations if you aren't paying attention.
Think about an assumption we literally make every single day. If you measure a piece of paper and call it 26 centimeters, you probably treat that as a definitive absolute fact, right? But mathematically speaking, a 26 centimeter measurement that's been rounded to the nearest whole number is actually hiding a range. It's not just a single perfect point, it's a whole interval of possibilities. So, here's our roadmap for today. We'll start with defining limits of accuracy, then look at sums and differences, move on to multiplying and dividing, and finally tackle some complex real-world applications.
Okay, Section 1. Defining limits of accuracy. Let's lay the foundation.
To really picture this, imagine a student, let's call him Ali, measures a sheet of paper at 26 centimeters to the nearest centimeter. That doesn't actually mean it is precisely 26.000. The true length just lives somewhere in the space closer to 26 than to 25 or 27. So that measurement sits exactly halfway between the next intervals. This means the actual, true value is floating somewhere between 25.5 and 26.5 centimeters.
And those boundaries have specific names. 25.5 is our lower bound, and 26.5 is the upper bound. But there is a super fascinating mathematical quirk here you need to know. The lower bound is officially included in this interval, but the upper bound, that 26.5, technically belongs to the next interval up. Because, think about it, if it were exactly 26.5, we'd naturally round it up to 27. But for the sake of setting our absolute mathematical ceilings, we just use 26.5 as the upper bound.
Let's ground this in the real world with example 10.1. A sprinter named Poor wins a 200-meter race. The stopwatch says 24.2 seconds, measured to the nearest tenth of a second. Well, the next possible times on that watch are 24.1 and 24.3. If we find the halfway points, his true time actually sits somewhere between the lower bound of 24.15 and the upper bound of 24.25 seconds. It's a tiny difference, sure, but in a sprint, those milliseconds are absolutely everything. Moving on to Section 2, Sums and Differences. Let's see what happens when we start combining these numbers. Check out these kitchen cupboards. Let's say we put a 300 millimeter and a 500 millimeter cupboard side by side. Finding the maximum total widths is a breeze. You just take the upper bound of the first one, 305, and add it to the upper bound of the second one, 505. Boom, 801 millimeters. Easy. But if you need to find the maximum difference between their widths, well, that requires a completely different strategy. And listen, this is exactly where so many people mess up. To find the upper bound of a difference, you do not just subtract the two upper bounds. Think about it logically for a second. To create the biggest possible gap between two values, you have to take the absolute largest possible size of the bigger item and subtract the absolute smallest possible size of the smaller item. It's a total crisscross. Upper bound minus lower bound is what actually gives you the maximum difference. Let's test that logic out. Say you have a red string and a blue string, and you want to find the minimum possible difference in their lengths, so the lower bound of the difference. You have to be systematic here. You take the shortest possible length of the longer string, its lower bound, and you subtract the longest possible length of the shorter string, its upper bound. By strictly following these steps, you completely avoid the trap of just blindly subtracting lower bounds from lower bounds.
All right, Section 3, multiplying and dividing. The rules shift again here.
Now, much like addition, multiplication is incredibly straightforward. Let's look at an A4 piece of paper. If you want the absolute maximum possible area, the upper bound, you just multiply the maximum possible width by the maximum possible length. Upper bound times upper bound. As you can see on the slide, 29.75 times 21.05 gives us a maximum area of just over 626 square centimeters.
But look at division compared to that. Division actually behaves exactly like subtraction. It relies on that same crisscross method we just talked about. Why? Well, it's the magic of fractions. Dividing by a smaller number always makes your final answer larger. So if you're hunting for the absolute maximum upper bound of a division problem, you've got to take the largest possible numerator, the upper bound, and divide it by the smallest possible denominator, the lower bound.
This cycling problem brilliantly shows the division rule in action. Look at example 10.3. Gan cycles 14.2 kilometers in 46 minutes. We know speed is distance divided by time.
To find his absolute maximum possible speed, we take his maximum possible distance, the upper bound of 14.25 kilometers, and divide it by his minimum possible time, the lower bound of 45.5 minutes. Maximum distance in minimum time gives us his maximum speed. Make sense?
Okay, if you only remember one thing from this entire explainer, let it be this cheat sheet right here. It perfectly summarizes exactly when you can use straight operations, like with addition and multiplication, and when you absolutely have to use that crisscross method for subtraction and division. Seriously, take a mental picture of this. It is your golden ticket to mastering these calculations.
Finally, Section 4. Complex real-world applications. Let's put this all together.
Whether you're calculating the population density of a busy town, which is just population divided by area, or trying to find the mass of a gold bar using density and volume, the exact same boundary rules apply to these scientific formulas. Because both of these involve division, finding the maximum bounds means you're going to be crisscrossing your upper and lower values again. So whenever you face one of these dense, complex word problems, just rely on these 3 steps. First, totally ignore the formula for a second and just find the basic upper and lower bounds for every single measurement given. Second, look at your formula to figure out if you're adding, subtracting, multiplying, or dividing. And third, bring in our cheat sheet rules to combine them. Keep your data neatly organized like this, and your calculations will be basically foolproof.
I absolutely love this advice because it hits the nail on the head. Math is not just about blindly memorizing a bunch of rules. If you're sitting there and suddenly freeze up, forgetting whether to use the upper or lower bound for a tricky division problem, just test the numbers out, calculate it both ways, and logically look at which combination actually gives you the biggest or smallest result. It is a fantastic built-in backup plan.
I am going to leave you with this final real-world mystery to solve on your own. In the 1983 100-meter sprint, Calvin Smith ran a 9.93, measured to 2 decimal places. But years earlier, Don Corey ran a 9.9, measured to 1 decimal place. At first glance, Smith obviously seems faster, but when we account for rounding errors and calculate the limits of accuracy for both of those intervals, is it actually possible the history books have the fastest runner wrong? Dive into the bounds and figure it out for yourself. Thanks for hanging out with me for this explainer, and remember to always question the numbers around you.